Okay, so welcome back. Today we are going to take the next step in our discussion of transformers. Previous video in this series we took a look at things like saturation and some of the nonlinear characteristics of transformers. In this video we're going to take the next step and we're going to try to do some detective work to figure out how we can model a transformer like this in a simulator software. For example, LTSpice or MATLAB Simulink. We're going to see if we can try and build a model that we can use in that simulator software. And then what we're going to do is once we built the model, we're going to verify it against actual bench testing. We're going to do some tests on this transformer and see if it matches our simulation. And what we're going to do is we're going to start out as a fairly simple model, and then once we have the simple model, we're going to implement some of the considerations we showed in the previous video. And again, I encourage you to take a look at that, where we're going to extend our model to show saturation effects and some nonlinear effects of the transformer, and we're going to test that versus bench testing to see what the results are and see if they match. So it's very important before you build a model for something like this or any piece of equipment that you define the operating range that you're going to be modeling. So for example, if I'm going to, as we showed in the previous video, if I'm going to be applying higher than rated voltage, I then need to consider the nonlinear characteristics of this. But if I apply only rated voltage, I don't have to worry about modeling all of that complexity. If I apply high frequencies, I'm going to have to worry about some capacitor modeling, where if I only apply 60 hertz, for example, I can ignore much of the capacitor parameters. So it's very, very important. The first thing you do, you figure out what range of currents and voltages and frequencies that you're going to be modeling, because that kind of defines what the model is going to look at, how complex it is, or how simple it is. Now, the next thing we're going to do, and I consider this a very important engineering approach with just about any engineering problem, is before you go start hooking up test equipment and measuring things, you first learn enough about the piece of equipment that you can figure out what you expect for results, even if it's just a ballpark. So, for example, we're going to have to model this as maybe an inductor with some resistances, and we're going to start out by saying, well, what do we kind of expect those values to be before we start hooking up our equipment? That way, if we make a mistake with our test equipment, and we all know that it's very easy to make a mistake with your scope settings or your power supply settings or wiring. If we make a mistake, we may get nonsense results that we think are legitimate. When in fact, if we had already checked what we expect for reasonable values, then we could say, hey, wait a minute, that doesn't make sense. We already looked at this and it should be something in this range. So the way we're going to approach this is we're going to take a look at this equipment and see what we can find with a little detective work to see what the expected values should be before we put it on the bench and test it. So if you look on this transformer, you can see that we've got some wire, some windings wrapped around this big heavy iron core. And this is about a 2-pound transformer. And we've got some windings wrapped around an iron core. And if you look in here, you can see a couple of sets of wire. And if you look on the outside, you can see a thicker wire. And it looks like it might be a copper tinned wire. And on the inside, you can see that there's thinner wire. And if you think about it, that makes sense because, again, this is a 120 volt to 12 volt transformer. The 12 volt winding is rated 4 amps. The 120 volt is rated 0.4 amps. So you can see that this heavier wire is probably the 12 volt secondary wire. And this thinner wire is probably the 120 volt 0.4 amp wire, all right? So now we know that we've got the 120 volt winding wrapped around the core internally, and wrapped around that 120 volt is a 12 volt winding. So we're starting to understand what we got here. Now, I've got here a piece of number 22 gauge wire. So if I hold that up to this 12 volt winding, you can see, yeah, that's about the same size, right? Maybe not exact, but at least it's about the same size. So we can start out knowing that this 12 volt winding is probably in the order of 22 gauge wire, all right? And then if you look on the inside, you can see, well, that's a lot smaller. So maybe that's, maybe 30 gauge or something like that. So that will be helpful because it will help us kind of figure out things like resistance. Now you can see there's a lot of turns on this transformer, okay? For the 120 volt, I can see 5 turns right away. And if you multiply that times this length of winding, there's a lot of turns here. So we know right off the bat, we're going to have to think about things like resistance. Even though it's just wire, there's a lot of turns, so there's going to be some resistance. And there's going to be probably a lot more resistance with the 120 volt winding because it's smaller wire, and probably a lot more turns. We also can figure out dimensions. So I've got these wires, and if I put up my ruler, it looks to be maybe a 1 inch by 1 inch iron core that these wires are wrapped around. So 1 inch by 1 inch means that each winding or each turn of this wire is going 1 inch, 1 inch, 1 inch, 1 inch. So it's probably about 4 inches of wire for each turn. So using that information, we can start to do a little detective work to figure out how much resistance the wire would have and maybe some of the other parameters. So what we're going to do is take a little bit deeper look on some of these physical parameters and see if we can figure out what we can expect for things like resistance and inductance of this transformer. Okay, so now we can see we've got these 2 windings wrapped on top of each other, and here's kind of a little simplified cross-section of what we've got here in the transformer. And the iron core is shaped like this. They call it inverted E's or upside down E's. Like you can see an E here connected with an E on the bottom. And around the center of this, we've got the 2 windings. We've got the 120 volt on the inside, and wrapped around that is the 12 volt winding. So you can see we've got this path of the flux generated in the windings that goes through these inverted E's. So here is in LTSpice the very beginnings of a model for this transformer. Here's our resistance of the winding conductors. R3 for the 120 volt, R4 for the 12 volt. And of course, we're going to have inductances of each winding, and there's a mutual inductance that we're going to model where the flux generated by this winding goes through the core and gets induced in the secondary to generate your 12 volts. So here is our basic model. So let's start adding some things that we have figured out so far to see where we are. Well, we know we've got 117 volts AC rating on the high voltage, 12 on the low, 4 amps on the 12 volt secondary, and 0.4 on the primary. So let's start looking at what kind of inductance we expect here, what kind of inductive reactance or impedance of this inductor, because we're going to have to figure out an inductance for this to model it. So we know that if I apply 120 volts to this winding and this secondary is open, there's no load, I don't expect a lot of current to flow, all right? This thing is rated 0.4 amps normal load current. So if this has got 4 amps of load current, we're going to see 0.4 here. So that tells you the current I expect with this with no load, with this opened, should be nowhere near as much as 0.4 amps, right? So this inductance is going to have to be a pretty big value. So if I apply 120 volts, and this is, say, 1 ohm, that's going to be 120 amps. So obviously this can't be 1 ohm. This is going to have to be a lot of ohms, which tells me I need a big inductance here. If I'm going to model this, it's going to be a big inductance because I only want to draw milliamps when I've applied 120 volts. So if it's 120 ohms, if this is 120 ohms, it's going to draw 1 amp. That's too much. So it's going to be a big inductance. Now we know that the impedance equals omega times L, and omega is 2 pi times the frequency. And we're dealing with 60 hertz, so 2 pi times 60 is 377 times L. So if my L is 1 Henry, the impedance will be 377 ohms. 120 volts over 377 ohms is going to be like 0.3 amps. That's not good because it's only rated 0.4 amps under full load. So we're starting to see that my L is going to be probably bigger than 1 Henry. It's going to be multiple Henries in order to get the inductive reactance at no load. So now we're starting to say, hey, if I make a measurement of this transformer at no load, I better see an inductance at 60 hertz that is significantly bigger than 1 Henry, okay? So now we're starting to see what we can expect here. Now, as far as resistance, okay, we got resistance of both windings because of all those turns of wire. Let's take a look. Here is a table of AWG wire sizes and versus how much resistance and how much current rating for the different wire sizes. Now we said for the 12 volt winding, we had something like a number 22. We compared it to the number 22 wire and said, yeah, that looks about like a number 22 wire. Well, if you look at the current rating for number 22, it's about 3 amps. Now, again, that varies depending on the type of conductor and all kinds of things and thermals. But ballpark is that number 22 is about a 3 amp rating. So we're in the decent ballpark because this transformer has a 4 amp secondary 12 volt rating. So we might think, well, maybe it's more closer to a 20 AWG, which is 5 amps. So for a good ballpark, let's assume that it's a 20 AWG conductor. You can get your calipers out if you want to get all excited about micrometers, but I don't care about that. I just want to get in the right ballpark. So I'm going to say it's about a 20 AWG, 5 amp rating, and this tells us how many ohms per foot, how many milliohms per foot. So it's 10 milliohms for each foot of wire. So we can use that to kind of guesstimate how many ohms resistance this would be before we actually measure it on the bench. As far as the 120 volt wire, maybe about 30 AWG. So if we look at the rating, that rating is about 0.5 amps. And we said at full load it's going to be about 0.4 amps. So that looks kind of reasonable. So that tells us if it's a 30 AWG, it's going to be about 0.1 ohm per foot. So we've got on one side, we've got 0.01 ohms per foot. And on the high voltage, we've got 0.1 ohms per foot. So now we can start to think about guesstimating how much total ohms we would see for those windings. So what I've done is I've gone to Excel real quick to calculate this out, to figure out the total ohms based on how many expected turns and how much total length of wire. So for the 120 volt on the inside, which is a 30 AWG, I figured about 4 inches per turn. Again, we said 1 inch by 1 inch by 1 inch by 1 inch. So one turn is about 4 inches. Again, a ballpark, but close enough. And we said 0.1 ohms per foot for this 120 volt. It's right here, 103 milliohms per foot. So I'm going to say 0.1 ohms per foot. Number of turns. This is just a guesstimate. So if you've got 120 volts and you've got 120 turns, that's 1 turn per volt. I'm going to assume more than that, maybe 400 turns for 120 volts. Again, it's a guess. I mean, you could go through the design to figure out what the more likely number is, but just for a ballpark, I'm going to say there's 400 turns in this primary. So with 400 turns, 4 inches per turn, that's 1,600 total inches of number 30 wire on the primary. 1,600 inches divided by 12 is 133 feet. So this means there's over 100 feet of wire on this 120 volt winding. So with 133 feet at 0.1 ohms per foot, we can expect somewhere around 10 ohms of resistance for this primary winding. It could be anywhere 5, 10, 15, 20, but it's going to be ohms. So if I measure in ohms and we get 1 micro ohm, alarm bells will go off and will say, no, 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 there's something wrong with my measurement. It should be on the order of ohms or tens of ohms, okay? And we can do the same thing for the secondary. It's probably going to be 1/10 of that. But this just gives us a decent ballpark. So now our model looks something like this with just kind of guesstimates. So I've got my 117 volt AC rated 0.4 amps. We figure that the inductance is going to have to be in the order of 5 to 10 henries in order to get enough inductive reactance to limit the current when I energize an unloaded transformer. So I'm expecting 5 to 10 henries for this inductance at no load. And we calculated in ohms of about 13 ohms. Again, it could be 1 ohm, could be 5, could be 13, could be 10, 20, but it's in that ballpark, okay? And same thing on the low voltage side, but there's going to be a lot less turns. So we're going to say maybe 1/10 of that for the resistance. And here's our model that we've got so far, just a ballpark. So now what we can do is we can go to the bench and do some measurements and figure out what the actuals are and see if they line up with what we expected. And if we don't get numbers like this, we can get alarm bells and say, hey, our measurement is wrong. So how are we going to do measurements? Well, we got to do resistance and we got to do inductance. Well, resistance, I can just hook up an ohm meter across my winding and measure the ohms. That should give us a good value. We could also take our DC power supply, apply 5, 10 volts, and measure how much current flows. And we could measure it with an ammeter or whatever current is coming out of the power supply. And that either way will give us a reasonable measure of DC resistance. I would tend to do both just to double check, make sure my ohm meter reading and my power supply reading are about the same, okay? So that should be fairly simple. Inductance, what I can do is I can apply AC and measure amps. So I can measure the amps with an ammeter in series with the primary winding, or I can measure the volts across a shunt resistor in series. And this is what we did in the previous video. We put a shunt resistor in series with the primary winding and measured the volts across that. And for example, we had a 0.5 ohm resistor and we measure the voltage across it, and the corresponding current would be 2 times the measured voltage since it's a half ohm resistor. So there's a bunch of different ways we can do this, and we just need to figure out which one we want or both. And again, doing both is good as a double check to make sure we're good. Okay, so now let's take it to the bench and see if my results match what I expect. So I've got my multimeter. I'm going to set it on ohms, and I'm connected up to the primary, the 120 volt. And you can see the ohms is 19.6. Now we said it was going to be around, our guesstimate was around 13 ohms, so 20 ohms is a good, reasonable estimate for the ohms. Now I can do the same thing for the secondary, and we said it's going to be about 1/10 of that. So I'll hook that up. All right, so it's about 0.4 ohms secondary. So now we've got a good idea of the primary, and we get 20 ohms and 0.4 ohms, primary and secondary. Okay, so now I'll use another method to check the primary resistance. I've got it hooked up to my DC power supply, and I will crank this up. And when I get up around 10 volts, I'll expect, if it's 20 ohms, it should be half an amp. So I'll go up to 10 volts, 8, 9, so 10 volts, about just under half an amp. So that makes sense if it's 20 ohms. So they both check and they both match what we expected. Okay, so now we're going to measure inductance. And I'm going to use two methods, both methods that I talked about previously. I'm going to measure RMS current directly in the multimeter. And I'm also going to use my scope to measure voltage across a shunt resistor. Now, be very, very careful. We're working with 120 volts. Don't try this at home unless you're qualified and you know what you're doing. Be especially careful. If you're working with a shunt resistor, make sure you use a differential probe, because otherwise you can short out your 120 volts by using one of the scope probes and putting ground. You can short across the transformer. Don't do it. So what I'm doing here is I've got my 120 volts coming in, as I described in the previous video. I encourage you to watch it. This red lead is the 120 volts coming in through the 0.5 ohm shunt resistor. I've got my differential probe going to the scope, and it's going out through this switch, this on-off switch. And this on-off switch comes out, then it goes through a fuse. This is a 0.1 amp fuse. From the 0.1 amp fuse, it's going through my ammeter right here, and then coming back and going into the transformer. So what I'm going to do is I'm going to turn this on and measure both on the scope and on the meter. Now the scope has a 50 millivolts per division, and since this is 0.5 ohms, we should expect the value of current to be twice what we see here. Again, it's kind of noisy, and that's why it's nice to have the multimeter, because it hopefully will clean up the reading and give us a more direct value. You can see with the noise here, there's 0 coming through the multimeter, so it's this is just noise. So it should help us to get a more accurate reading. So what I'm going to do is I'm going to turn on the 120 volt, and you can see here's the voltage across the shunt resistor, and it's telling me I've got 47 milliamps of current flowing into the winding with 120 volts. So that should tell you, should give you a very good idea about how many ohms this inductive reactance is. We said we've got about 20 ohms of resistance, but with 120 volts and only 47 milliamps, you can tell this is going to be over 2,000 ohms of inductance. So again, both of them are fairly consistent, and they give us a good idea that we're talking about 120 volts and about 50 milliamps. Okay, so now after bench testing and verifying that it met what we expected, for the most part, here is what we've got for a simple model of the transformer. We measured two different ways. We measured 20 ohms resistance on the 120 volt winding, probably got hundreds of turns of maybe number 30 wire, so that's about 20 ohms. The transformer inductance we figured out was a little over 6 henries, okay? We thought it should be in the 5 to 10 Henry range, and it was just about right in there. The way we got that is we applied 120 volts. We measured 48 milliamps. That comes out to 2,500 ohms. At 60 hertz, L equals 2,500 over 377, which is about 6 or 7 henries. So it all makes sense. The same thing for the low voltage winding is reasonable. So now we've got a simple model of the transformer to be used in the linear range at 60 hertz. Now our next step is going to be to look at the nonlinear range, where perhaps instead of 120 volts, we might apply a higher voltage, higher than rating, and per what we discussed in the previous video, we'll look into how you can model the saturation of the transformer so that we can apply higher voltages and see what might happen. All right, so in the previous video, we showed this chart here demonstrating how you can have a linear resistance, but we also mentioned that a iron core transformer does not have the same linear characteristic. In other words, with a resistor, it's always the same resistor no matter how many volts you apply to it. It's always the same amount of resistance, either 1 ohm or 10 ohms or whatever. But we said that a iron core transformer has a different characteristic at a certain point. So in other words, what we showed was a characteristic from 0 to say 10 volts applied across a transformer. It would be linear. In other words, it would act like a linear resistance, but it would be a constant inductance or a constant inductive impedance. However, above a certain amount of voltage applied to this transformer, suddenly the impedance, the inductive reactance of that transformer would drop quickly. So instead, in our case, we measured with 120 volts across this transformer, we measured about 47 or 57 milliamps, all right? Which meant it was about a 2,500 ohm inductive reactance of this transformer at 120 volts. However, when you apply more than 120 volts, suddenly it's no longer 2,500 ohms. It can be very, very low. It could be like 10 ohms or 1 ohm, depending on how much voltage you apply. So now the challenge is to figure out what is the characteristic of this corresponding to this. At what point does suddenly a little bit more voltage mean a whole lot more current? And ultimately, if you apply enough voltage here, this will be pretty much 0 ohms, and the only limitation to current flow will be this 20 ohms resistance of the winding that we calculated. So, for example, if I had 200 volts across here, we might get up to 10 amps because 200 over 20 is 10. So instead of the normal 47 milliamps, we might get 10 amps or 20 amps, depending on how much voltage. So our challenge is to figure out what kind of characteristic, voltage versus current, this transformer has so that we can model it. So what we're going to do is we're going to come up with something that looks like this. Again, this is just voltage versus current, and it is my guess at a characteristic that we can probably consider using. Now, where did this come from? Well, if you look over here, here's 0 volts, here's 120 volts. And what this says is that up to 120 volts, it's about a linear reactance, okay? It's acting like a linear reactance. However, at some voltage above 120, suddenly it's going to be very nonlinear and very, very low impedance, which means a lot of current is going to flow. So this is just a guess I made of a characteristic curve, it's called. So I'm saying that maybe at 130 volts, you're going to get up to, 3/4 of an amp instead of 47 milliamps. All right. So where do I come up with this? Well, I know that it's rated at 120 volts. Now, engineering-wise, you generally consider plus or minus 10% to be a typical range of accuracy. So 10% above 120 is about 130. My guess is that we can expect to be fairly linear up to maybe 10% over normal voltage. So that's maybe 130. But when you're getting much above 130, like 15 or 20% over, now you're starting to get into much greater than it's rated for. And perhaps the curve is going to look like this, and suddenly for a small increase in voltage, suddenly you get a big increase in current, right? So this is just a guesstimate, my guesstimate about what a voltage versus current characteristic would be like. And if we can enter that into our simulation software, we can have a pretty good idea of how it's going to respond at higher voltages. Okay, so now that we have the basic model and the concept about what we want to do for a nonlinear model, the question is, what modeling software, what simulation software are we going to use? And that's a bit of a difficult question. Now, here I've got LTSpice opened up, and I've put in my basic model of the transformer with I showed how to do this in previous videos, how to make a transformer model. We've got the resistance, and I've got the input voltage, 170 peak, 120 RMS, and then the 12 volt secondary. But if I want to do a nonlinear inductance in LTSpice, it's a bit of a science project. And yeah, honestly, LTSpice is designed more for electronics rather than real-world hardware equipment modeling like transformers and machines and motors and switches. You can do it, but there's other alternatives that I prefer. So I don't do the nonlinear inductors in LTSpice. You could also do it in MATLAB Simulink. Simulink has got nonlinear models. But again, they tend to, from what I've seen, they want to get involved in fluxes and a little bit more of a science project. I use a piece of software that is kind of designed for more power system machines, transformers, that kind of thing, and it's called ATP. And here is a simple model that I put together of the same transformer, but it has built in a nonlinear characteristic. So I've got a voltage source, I've got a switch, I've got my shunt resistor, my 0.5 ohm shunt resistor to look at the voltage across it, a differential voltage, and I've got my transformer, and I'm measuring inputs and outputs, and I'm measuring currents and everything else. And what I can do is I can enter in this model, I can enter a characteristic. And that's this characteristic we showed before. You can actually enter what you believe the voltage versus current characteristic would be based on, just your guesstimates of things that are real world. You don't have to worry about fluxes and, a big science project. So what we can do is we can enter that directly, and then we can simulate the transformer. So here I put in, here's current in RMS versus voltage in RMS. And I just picked some numbers. So basically, I know at 120 volts RMS, I'm going to have 60 milliamps. I think we had more like 40 or 50 milliamps, but whatever. And then I just picked some numbers below that for milliamps, like 1 or 3 milliamps. And then I kind of guessed at maybe 130 volts or 140 volts. I might get half an amp or 5 amps or 20 amps. So basically, I can look at this curve, and here's the curve I put in, and it basically looks like this. Again, it's not going to be super accurate, but it's going to give us a good ballpark for what to expect. Then what we can do is we can run this simulation for a particular condition, check it versus a real-world bench test, and see how well it matches up. So recall in the previous video, we did a simulation where I had my 120 volts coming in. I closed a switch and applied voltage to the transformer with an open secondary, no load current. And I measured it using differential probe across this 0.5 ohm resistor. I measured the voltage, which would correspond to the current flowing into this primary. So what I'm going to do is I've got this model set up with the saturation or characteristic curve I showed before, and basically the same setup. So I'm going to run this using this run command, and it runs the time step. And now I'm going to plot the results, and I'm going to choose the voltage across this 5 ohm resistor, which is this, and I'm going to plot it, and you can see I've got a result that looks quite a bit like what we got on the scope last time. And here's what we got on the scope last time. So you can see we've got this initial peak, and we recall it was limited by the 20 ohm resistance of the winding. And you can see you got this big peak, and it drops off very quickly. Now, of course, the relative magnitudes are a little bit different. But again, this is at 60 hertz. It matches up with this one. And it's got that initial peak, so it really is a great way to simulate and verify stuff from your bench tests. So again, we've got this nice nonlinear characteristic. So next what we're going to do is we're going to look at applying a higher voltage, higher than rated voltage, to see what happens on the bench, see what kind of currents we draw. Now I can go through and simulate that first by just changing this voltage. So let me change this value. I've got 120 volts RMS. Let me change that to 150. Okay, and I'm going to run it again. And we do the time step. And I'm going to plot. And I'm going to measure the same current going into the primary. And you can see, wow, I get these big spikes of current every cycle. All right. And you can see as let me also plot the primary voltage. And in red or green, I've got the voltage across the winding. And in blue, I've got the current. And you can see what happens is the voltage rises and the flux increases. And suddenly you get to a point where the current shoots up drastically. And then as the voltage on the source comes down, suddenly that shuts down because the flux has dropped. And now you're in negative territory. And you increase, the flux is increasing, and finally you get to the point where, again, it shoots up at negative, and you can see why this current goes up, because it's hitting saturation at each of these points where it suddenly increases. So again, what we can do is, probably in the next video, we'll actually apply maybe 150 volts and see if this matches our simulation. So anyway, I hope that helps. Take care and have a really good day. Thanks.